Good afternoon, ladies and gentlemen. It's a pleasure to be here, however virtually only. I would like to show you presentation Prospects to Monitor Potential Departures from Self-Arrested Ruptures using Near Real-Time Monitoring of Induced Seismicity during Hydraulic Stimulation. This presentation provides a summary of recent studies performed in Section 4.2 Geomechanics and Scientific Drilling at Helmholtz Center Potsdam in Germany. I would like to start this presentation with acknowledgements of the co-authors. This includes PhD students from our section, Maria Leonhardt, Stefan Benz, and Lei Wang, as well as my colleagues from the section, Patricia Martinez-Garzon, Marco Bonhoff, and Georg Dresen. Induced seismicity related to the development of enhanced geothermal systems, as you all well know, seriously affected or even terminated some recent geothermal projects, including Basel in Switzerland or Pohang in South Korea. Therefore, from this perspective, the implementation of safe stimulation strategies is vital and critical for the public acceptance of pending and future EGS projects. In this presentation, I would like to identify and show you outcomes from a handful of studies, pending and published, where we essentially wish to identify as cross-scale seismomechanical parameters that helps us to unravel the transition from stable to runaway ruptures. In the next few slides, I'll be talking about successful hydraulic stimulation in Helsinki, Finland, where using the real-time information from induced seismicity and geomechanics-based model of maximum magnitude, it was possible to control the induced seismicity and maximum magnitude. By controlling here, I mean maintaining the earthquake sizes within the limits of stable rupture propagation. For example, the maximum arrestable magnitude. The project site is located in Helsinki suburban area at the Aalto University in Espoo in Finland. This is 6 kilometers from the Helsinki city center, and the project essentially aims to provide a sustainable base load for the campus area heating network. 2 stimulation campaigns have been performed so far at the site. In 2018, 18,500 cubic meters has been injected at high well pressures of up to 90 megapascals to create the enhanced geothermal systems around the OTN3 well at the depths of 6 kilometers. This stimulation resulted in over 27,000 earthquakes with magnitude above -1. The second stimulation campaign has been performed in 2020 in the well OTN2 that is nearby, and this time 3,000 cubic meters of water has been injected and over 2,000 seismic events above magnitude -1 has been detected during that campaign. Waveforms were essentially processed in near real time, and that means that earthquake locations and magnitude estimations has been performed with a total delay between earthquake and the first break information on this earthquake not exceeding 5 minutes. And this information was then sent to the traffic light system operator as well as to the stimulation engineers to guide the pumping operations. The maximum observed magnitude was 1.9 and 1.7 for 2018 and 2020 stimulation respectively, both being below the red alert of magnitude 2.1 even specified for the site. For comparison, at Cooper Basin in Australia, magnitude 3.7 has been recorded at 20,000 cubic meters injected, whereas in Basel there were 11,500 meters cubic injected with maximum observed magnitude of 3.4 that led to the shutdown of the project. I will now focus only on 2019 stimulation and present you how the controlling scheme was essentially developed and implemented. So, well, first of all, at the very beginning of the stimulation in 2018, it was found that the seismic activity in the first injection phase that lasted 10 days basically occurred immediately after exceeding 70 megapascal wellhead pressure. It was also quickly realized that in this first injection phase, that the seismic energy release is proportional to the hydraulic energy that you can see here, which with the hydraulic energy being the product of pressure and volume. Also, it was identified that any stop in injection leads to the quick decrease in seismic activity. Second injection phase was performed at highest possible injection rates and pressures, and that led to the acceleration of seismic moment release that you can observe here, with basically a couple of large earthquakes occurring in that period of time that temporarily put the stimulation on hold. At this moment, the project team realized that the maximum magnitude evolution at the site increased with the cumulative volume injected, with the trend that is following the recent fracture mechanics model of Gallis et al. And while naively extending this trend, it was a serious concern of the project team that by the end of the injection at 20,000 cubic meters, the magnitude 2.1 red alert event will certainly occur. Model of Gallis et al. Provides the geomechanical base estimate of the maximum magnitude of so-called arrested ruptures. That maximum magnitude depends on, essentially in the model, on the amount of energy that is available, that is stored in the reservoir for earthquake nucleation and propagation, which in our case obviously depends on the hydraulic input rate minus generally unknown rate of dissipation of the energy in the system. So from that perspective, the project team decided to simply reduce the amount of energy that is stored at any moment of time in the geothermal system. Well, at first, the wellhead pressure in the following stimulation has been reduced to basically decrease the hydraulic energy input rate. And in the following, the injection plan was changed by progressively reducing the injection times and enhancing the resting periods to essentially stimulate the dissipation of stored energy. And that stabilized the seismic energy release with respect to the hydraulic energy input at the slightly lower level than observed before. And by the end of stimulation campaign, the red alert threshold was not exceeded. The successful control of the maximum magnitude was tied to the adaptive injection strategy guided by real-time seismic monitoring that essentially limited the rate of hydraulic energy. So, in other words, to stabilize the amount of elastic energy stored in the system. And the natural question arises here whether that can be actually applicable to any other EGS, which I will focus in the following slides. The success story of ST1 also was completed by the favorable site conditions, including structural inventory of the reservoir and stress conditions. And this I will not discuss here right now due to the lack of time, but feel free to look into our published and future pending studies. So in the follow-up study, we essentially investigated what's the evolution of seismic and hydraulic energy for a handful of enhanced geothermal systems, and that includes the projects cancelled due to the occurrence of large seismic events such as Basel or Pohang. And we investigated an evolution of various seismic parameters such as maximum magnitude, seismic energy, or seismic moment release in response to injection activities. So what was found here is that from most studies, the seismic moment release grow mostly linearly with the injected fluid volume, similarly to what was observed in Helsinki area. However, so what it means, so regardless of which model is used here, I painted basically Magar model or Gallis model of the maximum magnitude. So regardless of which model is being used, this stable behavior can be interpreted as stable rupture regime. However, for some sites, such as Pohang here in Korea, or Cooper Basin in Australia, where the large events occur, this evolution clearly depicts the persistent deviation from this stable rupture regime. So this study suggests that essentially the high resolution and near real-time seismic monitoring may help us actually to identify unstable state of the EGS system early on during the stimulation, provided that you have a sufficient seismic monitoring. And we identify the stable reservoir as those where the ratio of seismic to hydraulic energy, which is the seismic injection efficiency, is low or more or less stationary throughout the project. We also identify the cases where the seismic injection efficiency is growing rapidly, meaning that something is dangerous happening in the reservoir. However, I must point out two things. The care must be taken while using this information, as identification of potential dangerous trends is affected by the quality of seismic data selection and processing. And moreover, I need to stress out that sticking to the stable conditions does not mean that runaway event will not occur. This can essentially happen due to the unexpected structural conditions. For example, existence of major critically stressed faults on the perimeter of the reservoir that is expanding. To investigate in more details which parameters affect the transition from stable to runaway state, we perform an injection experiments in laboratory on two porous bentine sandstone samples. This actually studies has been published in two papers already authored by Lei Wang, and they are published in Geophysical Research Letters, so please have a look. The samples were first loaded to a critical stress at 35 megapascals, that's a confining state of stress, and in the following, the injection has been performed from the bottom of the sample in an undrained conditions. Two pressurization rates has been tested. For one sample, we choose the high and transient pressurization rate that is shown here. For the other sample, we choose a low pressurization rate that resulted in a pretty continuous injection into the sample. First interesting observation is that the total seismic energy release and mechanical moment seismic release corresponds essentially to the volume of fluid injected, which was the same for both projects. So basically, regardless of the pumping scheme, the ultimate cumulative seismic moment release from all events is the same. However, the way that seismic energy is released, that is shown here, is clearly different between the two experiments. And we found that the depth variations are related basically to the variations in hydraulic energy input rate. So for the low pressurization rates, so for the blue curve here, we have basically a stable fault creep that is visible throughout the whole experiment, with the stable release of seismic energy in acoustic emission data. For high pressurization rates, so for that curve here, that is actually magnified for a small part of the experiment in that picture, we observe the stick slip behavior with a transient fault creeping after each stick episode and the lock state of the fault before the large event occur. During the stick slip phase, the fault is moving and accelerated and progressively decelerating slip rate, and that coincides with accelerating and decelerating acoustic emission activity. We found that the seismic moment released during that stage is proportional to the cube of volume injected into the sample at that moment of time, during that moment of time. Whereas for the stable part, the seismic moment release is proportional to the volume of the fluid injected. So this overall means that the energy input rate guides the propensity of the fault to behave in this unstable manner. Okay, so here's the wrap-up of my talk. Several empirical parameters derived from induced seismicity allowed us to characterize the propensity of the reservoir to deviate from stable behavior. I would like to point out that any trends in seismic moment evolution that are observed with the real-time seismic monitoring that deviate from the predicted models of stable rupture propagation should be considered seriously by the operator, and they should potentially trigger a reassessment of injection operations. Our laboratory studies suggest that also we cannot really change the seismic moment that is released, that is caused by the fluid injection. We may be able, in some cases, to keep the seismic energy release stable by tuning the hydraulic energy input rate. And finally, the knowledge on background stresses, fault properties, and the hydraulic parameters is essential to model the fluid pressure migration and induced fractures, and special attention should be paid to the rupture from propagating outside of the pressurized zone. With that, I would like to thank you very much for your attention. I am looking forward for your questions. Here are my contact data if you would like to ask questions offline. And also I list the studies that are related to that presentation that are produced by our section. Thank you very much.